I'm Enrico Bonilauri. I'm the co-founder and CEO of Passive. And today I'm going to be talking about passive house in warm, hot, and humid climates. Before we get started on that, for those of you who don't know Emu, we started off the company in Italy, where I'm from, in 2009 as an architectural practice. We used to design buildings, and we did that for about 8 years before we moved to the company to the US in 2016. We adopted Passive House in the International Passive House Standard as our internal benchmark at around 2010. So we've seen the whole movement and standard grow and expand for about 15 years now. We are now based in Denver, and we are the main providers of hands-on passive house training across the country. We do some passive house consulting. I am a certifier for PHI, but really our focus is on passive house training with the intent to train builders, site supervisors, project managers, as well as architects and designers with a spin on hands-on training, because that is extremely important to get to the actual performance that you're specifying if you have that building built well on site. We see ourselves as a teaching hospital. We develop our own curriculum based on the consulting projects that we have, as well as the experience we have from Italy, Australia, North America. We have done consulting and projects, passive house projects, in every single climate zones of the US, and we reflect that in our curriculum. So we try to bring the international knowledge with all the climate-specific American variants to the training that we provide. Before we get started, we'd like to get a little bit of an insight from you. You have done that in the chat a little bit, but if you're an architect or a designer, please type one in the chat. If you're a builder or contractor, please type two. If you have some specialty, if you're a MEP engineer, if you rep Windows, if you work in HVAC, please type three. Or type four if you work in permitting, inspections, testing. We don't get a lot of you, so please type four. I hope you can see a lot of fours. Something else also in construction, please type five. And if you're not in construction, but you want to improve your own house, please type six. Or if you have a general interest in green building, please type seven. This is just a quick survey to see who we have here. Thank you so much for doing that. That gives me a little bit of an idea. We are going to have questions at the end. So if you have any questions during, please put it in the chat, and we're going to come back to it when we do the Q&A towards the end. Now, how passive are you? What is your level of current knowledge about passive house? If you're an Uber master, you know passive house in and out type 10. If you have certified a ton of projects, type 9. If you have certified at least one project, type 8. 7, if you are yourself certified, but you have not certified any projects yet. If you know what passive house is, type 6. If you're studying building science is 5. If you're new, type 4. And if someone told you to be here, type 3. 2 if you're looking for a career change, but you don't know yet. And then if you're really scared, just type 0. Just for fun, give yourself a passive house rating from 0 to 10. We cover materials in our presentations that is, it can be very advanced. This presentation is decently advanced because we talk about um, warm climates and humid climates, which have their own opportunities and their own challenges. So compared to what you may find from online, 3 things to do for passive house, or the top 5 passive house principles, the outcomes from today may surprise you because we are using the international passive house standard, but applied to warm and humid climates, which it's the same concept, but the outcome are going to be different. So thank you for that. These are the principles that I was referring to. We have super insulation, thermal bridge avoidance, high performance windows, air tightness, and heat recovery ventilation. If you think of what the 5 principles of passive house are, this is it. And these imply a better built building with greater energy efficiency. You get a lot of value out of these, but how much of this is needed for your project really depends on the type of project as well as on the climate. So the outcome you're going to see today are really geared towards warm and humid climates, and that's why it may be a little bit different from what we see typically. And the concept is that by adopting these principles, you really make your building into a thermos. A thermos is a well-insulated system. It's airtight, it's insulated, so it stays warm if it is warm, regardless of the exterior temperature, and it stays cool if it is cool in the first place, even though it may be hot outside, without additional active energy for heating and cooling supplied to it. Very unlike the coffee pot that you see here, that is more representative of a regularly built building that maybe just complies with the regular building code. It requires a constant supply of energy to remain comfortable. So thinking of passive house and its principles, what you really get out of it is a thermos building or a Yeti cooler building or whatever analogy you want to have, but it's a building that is a lot more detached from whatever is happening outside. And that is very important also for warm and humid climates. Out there, there's two main institutes that provide these standards. PHI is the International Passive House Institute, and FUSE Passive House Institute US is the US-based institute. The two, unfortunately, don't work with each other. They used to until about 12 years ago. And it was kind of a nasty divorce, and there's still some hard feelings at some point. But regardless of that, in the middle, you see all the different building standards that these institutes provide. Some apply to new builds, some apply to retrofits. Today, we're mostly going to focus on the international standard, although the FUSE standards is going to follow similar principles. Why passive house? We talked about the energy performance with the thermos analogy. What you get is stringent goals and a streamlined path to net zero goals or to electrification or to reducing emission carbon. It's also a much greater build quality because it has a much more stringent review of the design and the construction than a regular build building and more predictable results. You can promise a higher performance to your clients, but a lot of high performance projects don't actually meet those goals. These are some this is some data from the UK where the light pink columns represent the expected consumption of those buildings, and the darker red show the extra consumption of the built buildings exceeding what expect, well, consuming more energy than what the building was expected to consume. In other words, there was a significant performance gap over the majority of buildings they analyzed, except for the three passive house buildings that are on the far right-hand side of this graph, where the as-built energy consumption was pretty much identical to the design model expectation. So if you are trying to meet a higher performance goal, you need, in terms of net zero or emission reductions, you need to have more sophisticated tools, and Passive House provides this more advanced building science to have a more detailed expectation that is going to be met by the actual performance of the building once it is built. There's thousands of passive house buildings that are built and occupied in different climate zones of the globe. Passive house has been around since the early 90s. There's a lot of buildings in Europe. China is huge on passive house, on the international passive house standard, but there's passive house buildings in hot and humid climates in India, in Southeast Asia, in Australia and in the US, of course. So that really applies to multiple different climate zones. In addition to the greater energy performance, it also provides greater living conditions compared to regularly built buildings. And that is one of the aspects that I, as an architect, find more attractive of the standard itself, because you have a much greater indoor air quality. We're going to see more of that later. You're going to have a much higher thermal comfort, which for climates like what we're talking about today is still relevant, but it is less crucial than colder climate zones. We're going to talk about that also. Avoidance of modern condensation, as well as passive survivability. How long a building remains livable before, once the power goes out, before it becomes too hot or too cold to live in compared to a regular building. So those are all improvements on the regular building that passive house brings to the table. Now, why is this important also in warm, hot, and humid climates? You see a picture here from the Texas energy crisis from a few years ago. And, you know, just to expand beyond the operational carbon emissions and cost, that is the most obvious advantage of adopting passive house. You get better living conditions, but it also is a more resilient path towards electrification. The more we switch to electrification, the least resilient our buildings become because they all converge onto one energy vector that is electricity. And once that fails, it's very hard to come back. And if your building is like a coffee pot that needs a continuous supply of heating or cooling to stay livable, that building will become unlivable very quickly, as opposed to a building that is like a thermos. It needs just a little bit of energy to stay cool or to stay warm. When the power goes out, not if, when the power goes out, that building will remain livable for a longer time. This is a study from Houston showing the increase of, sorry, the decrease of resiliency the more we are going towards electrification. In other words, going towards electrification for buildings is great on one side because we can use renewable electricity better, but it also becomes less resilient because we are converging onto one vector. And that is where we want to have the building become more passive house because it becomes less dependent on the grid being on at all times. This is the passive survivability, and this is a map of Texas where, if you think of passive house in the US, Texas is probably not the first state that you can think of, but this is a graph from the 2021 Texas power crisis showing the number of customers without power. And that is hundreds of thousands of people left without power for a long time. And if you have just switched to an all electric building, you're out. And your building will become cold or will become hot very quickly unless you use passive house strategy for your building envelope. So this is why, in the bigger picture of making our built environment more resilient, passive house is a key component of the strategy, even in warm and hot climates where your heating bills may be less impacted by the savings provided by passive house, but the passive survivability is greatly increased because your building is more passive house. So some examples from around the world that are unfortunately not that known in the US. This is a build. It's an office building in Dubai, built about 10 years ago. I know this building very well because the HVAC engineer that did this and the passive house consultant that worked on this project is actually a very good friend of mine from Italy. But this building is in one of the hottest and most humid places in the world, that is Dubai. It's certified passive house. It's a non-residential building, and it has been occupied since 2015. They did 3 years of intensive monitoring for the consumption, and they showed that it was very close to what PHPP was matching. So if you think of the international standard, it's really been applied across different climate zones for a long time, and that provides a very solid standard to begin with, even for warm and humid climates. Other examples, this is a retrofit of a factory in Sri Lanka. And then in the US, we have a lot more single-family homes at the moment, not as much commercial projects, but it's about to come. So I don't have any doubt that the same model will work also in hot and humid climates in the US. For this study, we identified 10 different locations across the US that could qualify or would fall under the definition of warm, hot, and humid climates. And what we did was we wanted to look at improving living conditions inside the building. We want to increase resilience and passive survivability, And lastly, we wanted to look at the reduction of operational carbon and costs. And to do that, we took a small multifamily project that we had worked on in the past. This is a 14 apartment building that we took and we placed in these 10 different locations to see how much different passive strategies would improve on those conditions, the passive survivability and the operational carbon. So we took this project and we moved it around the country to kind of see how much different strategies would benefit this project. So the reference project is a multifamily project for 14 apartments, 36 people occupancy, about 12,000 square feet true to floor area, and about form factor of 1.9. We're going to see later what that means. That this is the typical floor plan. It's a two-story building. This is a typical section. And what we did for the project was we decided to use the attic space as the mechanical space. So the upper boundary of the building is actually the roof, is not the ceiling. That is one of the peculiarities of this project, as well as we have interior corridors that distribute individual units, but we were able to enclose all of that into one building envelope. In other multifamily projects we have worked on in California, for example, um, sometimes the developers want to have the apartments being accessible from the outside individually, and that makes it harder to meet passive house just as an overall air tightness strategy. So that's something to keep in mind if you're working on the concept of an architectural project. They're looking at different climate zones. We look at the we looked at a little bit of a comparison between PHI and Fuse allowances. The Fuse keeps on saying that they are the only climate-specific standard. That is not true with regards to the cooling demand. And this, the first blue column on the left under the PHI allowances shows the climate-specific allowances for heating and dehumidification under the International Passive House Standard. So that is something that hopefully the narrative will change. And I put together this table just to compare them. Um, what it is important to see here is that PHI requirements are significantly more stringent than Fuse requirements. That is true even in warmer climate zones, and it's pretty much true across the board as far as the studies that we have conducted. If you're interested to learn more about the comparison of the two standards, we have a whole presentation and a standard that you can download from our website, the IMU report on building standards. That is a white paper we published a couple of years ago. It's available for free download on imupassive.com. I don't want to spend the rest of the presentation comparing the two standards. We're mostly going to look into how individual passive strategies can benefit the buildings in these different climate zones. So starting off from the living conditions, we started off with looking at indoor air quality, thermal comfort, and passive survivability. Now, indoor air quality, if you ask most people that are not in construction, high indoor air quality is one of the main concerns that they have, regardless of the energy efficiency of their building. We assumed 15 cubic feet per minute per person continuous fresh air supply. And this is something that will come up handy if you want to win the quiz that we have later. But it is something that we assumed as far as the project requirements to have a continuous supply of filtered fresh air to the amount of 15 CFM per person. That is to maintain the level of CO2 below the threshold of 1,000 part per millions. In addition to that, we're going to also look at the particulate matter 2.5 a little bit. Particulate matter 2.5, for those who don't know, are very, very small particles, solid particles that are suspended in the air that can cause cancer because they're so small they can get into the bloodstream and cause cancer. And so this map here shows a 1 day concentration from NASA. And we looked at that. It causes between 100 to 200,000 deaths per year in the States alone. So it's something that if you try to build a building that can protect people, limiting the exposure of exterior particulate matter 2.5 is a significant step in doing so. We looked at the different requirements for air filtration and air leakage allowance for different building standards. And on the left-hand side, you can see the outcomes for this type of building, where the combination of the ACH 50 requirements and the filtration grade requirements for each different standard results in the effective filtration grade shown on the graph on the left-hand side, with PHI providing a lot higher protection because it's a lot more airtight, and it requires higher filtration grade and MERV 13 filter, as opposed to Fuse has a similar air tightness requirement for this project, slightly higher allowance for air leakage, but their filtration requirements is a lot lower. They only require a MERV 8 filter, which only filters out 20% of the particulate matter 2.5. If you're interested, actually tomorrow night we have a presentation, again, free on Zoom, about passive house and indoor air quality. We're going to cover this in a lot greater detail. You can go to newpassive.com, find the calendar, and sign up for that. Again, I don't want to dive too deep into air quality today. There's a lot more to cover. But if you want to expand on passive house and indoor air quality, we have a presentation for free tomorrow on Zoom. Thermal comfort was the second piece of improving the living conditions for this project. And in life, you can assess thermal comfort conditions by using one of the significant metrics of thermal comfort, which is the U value, well, the surface temperatures of the building component of the building envelope, and windows and exterior doors play a major role in this equation. This graph shows the average interior surface temperature on the interior surfaces of windows and exterior doors in different locations, depending on which building standards we are adopting. In this case, specifically, we were looking at Fuse PHI IECC, the 2024 IECC, and Title 24. And you can see that Fuse and PHI all keep the surface temperatures above the threshold for thermal comfort that is set at a delta of 7.6 degrees within the room temperature. As you can see, the requirements for Fuse are also in this case are more relaxed, but because the climate zones that we're looking at here are fairly mild, they pretty much all are around the thermal comfort. What really fails to meet the comfort requirement is the IECC, and even in warm climate zones like Austin or Orlando, Florida, or Phoenix, the IECC, International Energy Conservation Code, really does not address thermal comfort at all. The U values that IECC prescribes are too high, so too high heat losses allowed for windows, so that the interior surface temperatures are too low, and you end up being cold and uncomfortable, even in cold climate zones, even in warm climate zones. I'm sorry. I'm going to pop up this towards the end because on next week we have a presentation on Zoom about Windows and thermal comfort specifically. I don't want to pitch just all of our presentations, but we do a lot of free presentations to talk about building science and these aspects of value. And so next week, August 27th, we have a presentation on Zoom on passive house windows and thermal comfort, if you're interested in learning more about this. Switching to the passive survivability and the increase of resilience, we talked about the thermos versus the coffee pot, and the difference is that if you apply the passive house principles, your building becomes more like a Yeti cooler or a thermos, and so it will be keeping the heat or keeping the cool inside, even if the exterior conditions become extreme. And that is without supplying energy, as opposed to a cold-built building where you need to constantly supply energy to keep it cool or to keep it warm. Now, from a practical standpoint, we have a couple of examples. This is the Icebox Challenge that PHN does around the country. This is when they were downtown Denver a couple of years ago. they built one icebox to comply with code and another icebox to comply with passive hours. And what they found that this was in the summer, the passive house icebox lost about half of the ice. They fill it with ice and they let it cool down they let it melt for a week or so without any active cooling. And the building built to the just regular building code lost twice as much ice. It allowed twice as much ice to melt over the same amount of time compared to the same icebox built to the passive house standard. This is an example of resilience in warm conditions. And for resilience in cold conditions, uh, same principle. These are the pods that we use in passive house training when we train builders and architects on site. And we heat them up. These are uh, the same size. They apply insulation, air sealing. They have high performance windows. And what you're looking at the red light is we are warming them up to test them. And we heat them up for a certain amount of time, and then we switch them off. And one of these pods is built to the code standard. In this case, it was the 2021 IECC. And this is the heating time. At some point, we turn the heating off. And what we see consistently over and over again is that all pods that are built to the passive house standard keep the heat better, even if there's no more active heating, compared to the same pods if they were built to the 2021 IECC standard. So this is an example of the opposite of what we saw earlier. This is the hot box challenge, but this both of these empirical cases show that if you're building your building as a thermos, it will keep the ice or will keep the cool. It will keep the heat for longer compared to a regularly built building. And this is how it's a way to make your uh, built environment a lot more resilient. So when the power goes out, not if, when the power goes out, if your building has these passive house principles, it will remain livable for a lot longer. That is what we learned that Houston or the Texas buildings did not have in 2021, and we can only hope that passive house becomes part of the electrification process because it makes our built environment a lot more resilient. Now, uh, switching off to the reduction of operational energy and operational carbon, we took the same building over these 10 different locations, and we looked at this is the baseline of building to code minimum for the IECC requirements, and we looked at California Title 24 for the few locations that we had in California. And what we did was we used PHPP, the Passive House Planning Package. It is the main tool used internationally um, to design passive house buildings, which is also, by the way, validated according to ASHRAE Standard 140 for the US. And we had the goal to evaluate the reduction of energy and carbon emissions. One thing that is important to know is both PHI and FUSE have their certification parameters set at 68 degrees set point temperature for wintertime and 77 degrees set point temperature for the summertime. For this study instead, we use some more American, or what I have seen being more used by Americans in the buildings, of 70 degrees set point temperature for heating and 72 for cooling. And there's a couple of examples we're going to see today where this is going to be impactful in the outcome and what we decide to do with our building. So it's something to keep in mind that both PHI and FUSE use the same set point temperatures, but for this study we use a narrower span of temperatures to see that because it's empirically what we have seen in our consulting projects. So the goal is to have an all-electric building for heating, cooling, dehumidification, and fresh air systems, meaning that it's all electric. We are modeling air source heat pumps for heating and cooling, and we are using additional dehumidification decoupled from sensible cooling. This is something that for humid climates, going from Austin to New Orleans, Orlando, if you want to be efficient, you want to decouple your dehumidification from your AC. because sometimes you need to just remove moisture, but your temperatures may be okay. And this is something that we can talk more about this in the Q&A later, but that is what was one of the assumptions of the study, where the dehumidification was separate, basically was a recirculation system that was separate from the sensible cooling, and it was separate from the fresh air system. The fresh air system we had because, as I mentioned earlier, in order to have indoor air quality, we assumed a continuous supply of fresh air of 15 cubic feet per minute per person. And that is going to be also very significant when we look at the outcomes. But that was a primary goal of the building, was to improve on the living conditions, so have high indoor air quality. We wanted to meet that goal, and to do that, we need to have a continuous supply of fresh air. So these are the kind of the background of the system that we looked at. Now, um, we something that we can geek out about, but I'm not going to cover too much about today, is the efficiency of the heat pump in different climate zones, in different conditions. But I don't want to spend too much time on this today. These are the conditions, these are the climates. And it's easy to say, oh, my climate is warm, my climate is hot. But another thing is to try to measure that. And so this is a comparison of the heating and cooling days for different climate zones. We have mild climates, Los Angeles and San Diego. We have a climate that may be labeled as warm, San Francisco, but that's because it's not warm, but it's not cold either. So it's a there's not much heating needed, but it is a heating dominated climate. So it's kind of a weird climate in itself. Opposite to the hot, dry climate that is the cliche of Phoenix, very hot, very dry. You can see the light blue here represents the sensible cooling, as opposed to the dark blue represents the dehumidification, so the latent cooling, as opposed to the orange that represents heating. Then we have a third heating, a third cooling, and a third dehumidification climates that are Dallas, Austin, and Atlanta. Something I need to say here is that in this graph, we are also considering the efficiency of the heat pumps. So heat pumps, as I mentioned earlier, are a lot more efficient in producing cooling than they are in producing heating. And once you look at the climates through those lenses of providing heating and cooling and dehumidification through a heat pump, this is what the graph looks like. So Austin, you may think it's a very hot climate, but for a heat pump, the heating part is significant because the heat pumps are not as efficient in producing heating as they are to produce cooling. And then you have the hot and humid climates, Orlando, New Orleans, Corpus Christi, where you have a lot of dehumidification, basically no heating. So this is kind of like what we found of these climates, and that is significant in the outcomes we're going to see. The passive house strategies that we identified were super insulation, thermal mass, ground coupling, we're going to see what that is, air tightness or air sealing, high performance windows, solar control, meaning shading and passive solar gain control on the glass, heat recovery ventilation, and we are not addressing thermal bridge avoidance here. In other words, we took the 5 principles of passive house that we covered earlier, and we dissected them and we divided them in ways that we could assess their impact individually on the reduction of heating and cooling combined for these projects. So we're going to look at adding insulation by itself. Then we're going to revert back to the baseline. We're going to look at thermal mass by itself. We're going to look at ground coupling by itself, so on and so forth. Now, the thermal bridge avoidance, that is something that we have assumed some regular amount of thermal bridging due to stick frame construction for this kind of project. We don't have a way to assess the risk for actual thermal bridging caused by building code not addressing that. So that is we left that kind of on the side. So quiz time. Please put in the chat of these 7 principles, which one you think is going to be most impactful. Please take a second to enter that in the chat, and let's see what you think is going to be the most impactful for this. I see air tightness, I see air tightness again. C3 air tightness, I see solar control, I see windows, air tightness, good, good. Super issues, excellent. And as many things, I didn't know. We did this study and we identified these principles. Thank you for putting that in the chat. But it's hard to say, oh, it's going to be always air tightness, or it's going to be always shading because it's a hot climate. There's so many parameters that where the logic, where we think uh, has to take a step back, and we need to look at the more advanced building science and the energy modeling to give us actual answers. Literally, we started this project, this research project, because we wanted to present on passive house in hot, warm, and humid climates, but we didn't know the outcome. So this was a good exercise to do. And thank you for that. And I bet that some of you are going to be surprised by the results. So look, starting from the super insulation, we started off with the baseline. For the projects located in California, we use the Title 24 requirements for the baseline. For the other projects, we use the 2024 IECC requirements for the baseline. And then we added R10 to the floor, exterior walls, and roof. And then we added R20 to the floors, exterior walls, and roof. And then we added R30. This is just us trying to map out what was most impactful in terms of combined heating, cooling, and dehumidification. And this is what we got. Number one is the baseline. Number two is when we added an R10. Number three is when we added an R20. So you see the first R10 is a better reduction compared to adding an R20 or an R30. We start seeing some diminishing returns. And so this is where going to a very high R value in this climate zone may not be super effective because you have some diminishing returns. It may be in combination with other parameters which you're going to see. But this is all results for each of these locations using PHPP data. That is what we did in the background to get these numbers. And again, this is the combined site energy for heating, cooling, and dehumidification. We are not looking at lights. We are not looking at domestic hot water. We are just looking at heating, domestic hot water, and dehumidification site energy. Then second, we looked at thermomass. And we looked at thermomass because it's a very popular concept. We started off with a baseline of no thermomass, meaning that the walls are stick frame, the ceiling is your trusses, and your floor is a framed floor. We then switched to a concrete slab at the bottom, and then we switched to all walls also mass. So we went to an extremely lightweight building of the baseline to a decently lightweight building with a concrete slab and to a very cave, like extremely massive wall. And these are the outcomes. So there's not that much reduction allowed by thermomass in terms of site energy for heating, cooling, and dehumidification. We're going to see in the context overall what that means, but thinking of hot climates and thinking of passive house principles, you may come across thermomass. And if you start looking at the actual numbers from thermomass are rather disappointing. If you look at the actual numbers. Then we switched to ground coupling, meaning that at the bottom of the building, you see the building section on the left. We started off with the baseline of the amount of insulation that the building code requires, and then we removed it. We went to an R0 to see whether or not that ground geothermal energy would allow to suck the heat out of the building or not. And then we switched to an R10, R20, and R30 just to see how much that impacted the building. And again, this is a building with a fairly large footprint because it's a multi-family building of only 2 stories, so it's a pretty wide building. And so the goal was to try to identify if removing that insulation and coupling the building with the ground in these warm climates was going to be effective. And this is what we found, is that removing the insulation under the slab was actually worse than the baseline. And something that we've done this exercise before. And remember when we started off this conversation where PHI and Fuse both have the set point for cooling set at 77 degrees temperature. And in that case, if you have your set point temperature around 77 or 78 degrees, removing the insulation under slab would be better, would reduce the need for heating and cooling. But because we are looking for more realistic set point temperatures for the American market of 72 degrees, because people like it cool, then you get gains even from this slab up. And so you want to insulate your building from that. That is something that they learned with the Dubai project. So they literally had very high passive ground gains because the ground is warmer than the temperature they want to keep the building at. And so this is something that is very important if you're trying to get buildings to passive standard. Keep an eye on the certification goals, but also keep an eye on the actual used conditions because you may have a contrast between those two. So this is what we saw for the ground coupling part. Then we have the air tightness, the air sealing. A lot of you put that in the chat. So we started off with the baseline. We went to 2 ACH 50 air changes per hour at 50 Pascal during the blower door test. We went to 1.5, we went to 1, we went to 0.5. And that is what we found. We're going to see if this is going to be the winner of this comparison. A lot of you are betting on this. Then we looked at high performance windows. We already looked at the impact on thermal comfort. And we started off with the baseline of code minimum window performance. We did a skinny triple pane glass. We went to a beefy double pane glass, beefy triple pane glass. Unfortunately, we don't have the time to go over that today, but next week we have a presentation just about that. We went to C, B, and A grade triple pane glass. We assume 0.25 solar heat gain coefficient for all of them. And this is the reduction that we see. So moving away from the baseline is good. Double pane glass, beefy double pane glass performs better than skinny triple pane glass. That's something that you want to be very careful about avoiding to buy. But this is the results we got. Then next we got the passive solar control that is 0.25 solar heat gain coefficient with no adjustable shading. Interior adjustable shading with 0.25 solar heat gain coefficient. So we looked at changing the interior and exterior shading and changing the solar heat gain coefficient, and that provided some improvements. And lastly, something to keep in mind in hot climates is that if you're going to low gains glass means you're also going to get a lot less daylight. Or most low gains glass has low visible transmittance VT. So that's something that you want to keep in mind because you want to have a visible transmittance of at least 0.6. Otherwise, your rooms are going to look very dark. This rendering here is for my own living room up in the mountains, and I just wanted to go to show a comparison of how little daylight you get if you're going to low gains glass. Just something to keep in mind to have a holistic approach to the matter. Lastly, we looked at the heat recovery ventilation. Keep in mind that we had the 15 cubic feet per minute per person continuous fresh air for this project. We looked at the baseline of no heat recovery, then 50% sensible recovery, 0% latent, 90% sensible, 0% latent, 50-50, and then 90 sensible and 90% latent. So different types of ERVs and HRVs. And what we saw was some significant amounts in reduction for the heating and cooling combined because we are supplying the building with that decent fresh air supply per person. So if you're looking at all of these individual outcomes in the same synoptic view, this is what they look like. And where we see the diminishing returns of the R values and no diminishing returns for the air tightness. So there is no diminishing returns to air sealing more. So air sealing is more convenient than adding R value unconditionally. Again, depends on a little bit on the type of project and the goals that you have. Then we saw that the thermal mesh was by far the least effective strategy. This may break some hearts, but we see almost no changes from going to an extremely lightweight building to a massive cave-like building. The third most effective was the increase in the R values. The second most effective was the increase in air sealing. And the one most effective was the heat recovery ventilation because we were prioritizing indoor air quality by means of supplying the building with continuous fresh air. This is some may be surprised by this, but this is what the data shows us. So we need to have an adult way to look at data by means of the energy modeling done in PHPP. Um, how does that compare to what you were expecting? Do you have put that in the chat real quick? Were you surprised? Are you shocked? Of course, you knew that. Put that in the chat. See some interesting, surprise. Excellent. I was surprised myself. I was expecting the air tightness and heat recovery to be up there. Um, good. And at the end of the day, this is like looking at a model, PHPP, that has been validated over thousands of projects over 30 years and how to use that. But hopefully this allows you to look at the whole picture in a more structured way. We looked at an example of adding R10, going for 0.5 ACH50, which for a building this size, that's pretty straightforward to do. It's not that hard to get to 0.5 ACH50. And looking at very high heat recovery ERV, um, and this is what the heating demand, so the site energy demand for heating, cooling, and dehumidification was. And once you applied this combined insulation, air tightness, and ventilation heat recovery, this is the reduction. We get about 40% reduction. So it's significant. And on top of that, you get a lot better living conditions inside the building. This is not necessarily meeting the passive house certification goals, but it's a way to show that even changing some parameters, but knowing which parameters to change and how much, it will be very impactful for the efficiency of the building. Now, how do we measure success? This is, of course, each location has different cost of energy, CO2 emissions for that energy. If you were to invest in PV systems instead, the output would be different. So we looked at these parameters, and this is the reduction of the site energy demand for depending on each project. If you're looking at the operational carbon emissions, it looks different because the different grids have different carbon emissions associated with them. If you're looking at the operational, uh, this is dollars per year per apartment, cost saving, as opposed to the PV panel saved or the amount of trees that would correspond to using this. 70 trees installed in Los Angeles or 700 in Corpus Christi. So there's different ways to measure success, and there's not only one. But what is important here is that to understand that there's a lot of that goes into it. So to conclude, passive house is a way to really improve the living conditions inside buildings, even in warm, hot, and humid climates. Passive survivability is a huge plus because it allows buildings to be more like thermos, and they provide a durable, livable shelter even when the power goes out. The effectiveness of different strategies varies depending on the type of project and on the climate, of course. Then the approach has to be performance-based. There are some prescriptive approaches out there that are really not addressing the issues. In fact, in the report on building standards, we have a whole comparison between a prescriptive approach and a performance-based approach. And the performance-based approach ends up to being cheaper dollar-wise, even once you include the cost of the energy modeling compared to the prescriptive approach. So it's a complex scenario, but Passive House provides the building science handrail to navigate through this. If you're interested to learn more, this is some training options that we have. I know that most of you are from the golf course, but this is the training that Blake was referring to. And these are the presentations that I was referring to myself. Tomorrow we have one about indoor air quality. Then next week we have one about high performance windows and thermal comfort. And then September 9th, we have a panel discussion with passive house builders in California. So if you're interested, all of these are listed on imipassive.com for the events calendar. And now I'm gonna put in the chat the link for you to claim your PHI continuing education credits. And I'm available. We're almost at the time, but I'm available to take questions. Thank you so much for listening. I know I talked a lot.